Welcome back, guys. We have covered a number of interesting topics so far related to inter-process concurrency. We've seen how to create processes, forking them, executing new code in their address space. We've seen pipes, we've seen sockets, and today we're about to embark on a new topic, which is none other than shared virtual memory. So without further ado, let's jump into the slides and start looking at that. All right, so shared memory, a very interesting topic in its own right. You'll see that it's quite straightforward, and we'll go in stages as we discover the topic. So what I want to do first is give you a little bit of an idea of why people introduce shared virtual memory and what kind of problems it addresses. Then we'll look at memory maps, shared memory itself, and synchronization primitives, and that should pretty much wrap up the topic. All right, so think about it. We're talking about memory mappings for the most part. That is, we've discovered multiple ways to do I/O. For example, there is the entire F file, system call API family for opening files and have buffered I/O. We've seen the file descriptor API, open, close, read, write, dump, all these guys that are great for setting up pipes and for doing unbuffered I/O. And we've seen like, okay, that's great, but this is still manipulating files for doing I/O, and those are completely file-centric. They give us a stream of byte, and with file APIs, we can do things like go back at the beginning, we can rewind, we can seek to go to a specific address and then start reading. That is, there is this smell of 1970s, 1980s, where these files were on tapes. Rewind, even the name is just rewinding the tape to go back at the beginning and start reading sequentially. So they really have a sequential flavor to them. If you want to do random access, it's kind of a pain in the neck because you have to seek and then you have to do your reads and writes. So this is not necessarily the best thing we can do. Now, we're about to actually change that and see that we can have a much, much better API to do this. And the reason is that files, at the end of the day, they just represent memory. We want to have a mechanism to access memory in a unified way, whether it's a file or whether it's a memory block into our address space. Why should it be any different? Both are forms of memory. And that is the interesting bit. Now, of course, that's a good question. Why can't we do that? And of course, people have asked this question, and the answer was a resounding like, well, there is no reason why we can't do that, and therefore let's do it. And people have created the necessary API, and that's what we're about to discover. Now, if you recall what an address space looks like, it's this picture that we see here on this side, right? So an address space is a fairly big block of memory where we find the code down at the bottom, if you recall, the static variable right above it, the heap, which grows upward, and then the stack that grows downward. Now, you need to realize one thing, is that this drawing is not to scale. Indeed, if you think about the program, even the big one, like Microsoft Word or something like that, maybe it's like 50 megs to 100 megs of code. Maybe that. Maybe that's another 50 megs to 100 megs of heap allocated data structure, and it's a couple of megs of stack. Give or take 250 megs for it. That is nothing compared to the size of a 64-bit address space, which is 2 to the 64. This is substantially bigger. So this, just like outer space, this gray area is empty. There is nothing in it. On a 64-bit machine, it would take forever for these two guys to actually meet in the middle. You would have to allocate 2 to 64 bytes, which is an insane amount of memory. So this does not happen in practice. So this is great. This is completely empty, and we're going to take it to our advantage. Namely, we're going to say, if it's empty, why don't we take a file and slam it in here, pretend that the file is in memory, and then start accessing the content of the file. And that's exactly the idea. That's what we do. We're going to take a file and map it into the gray area so that we can access it as if it was normal memory. So that's the idea. That's what we're going to do. So I'm going to go into my disk where there is a file. Here's my purple file. And I'm going to ask the operating system, please take that file and put it up there. Now, again, this is not drawn to scale. A file, even if it's a 4 gigabyte file in a 2 to the 64 address space, is still a tiny, tiny sliver. So this definitely doesn't use up a huge amount of space in the gray area, and it's unused anyway. And once it's there, then we can use pointers. We can just go in that area with our trusty pointers and start accessing this as if it was an array of bytes and do whatever we want. That's the key idea behind virtual memory and memory mapped I/O, right? Which is exactly what we're going to do here. So there are two APIs to do that, and we'll dive into the details pretty soon. One is called mmap, memory map, to create such a mapping, and the other is munmap, to destroy such a mapping. Because as always, if you acquire resources from the operating system, you will be expected to let go of these resources once you're done. Now, a couple of things that are important to know about this API, and they are listed here, right? When you actually do an mmap, you have the option to ask where it will go in the gray area. So you can give an indication of where you want it to be. You could pass null, in which case you say like, I don't care, place it anywhere where there is room in the gray area. One caveat though is that if you give a location, that location needs to be page aligned. Now, most operating systems on Linux, for example, a page is 4 kilobytes, 4096 bytes. So it means that the address of a page starts at 0, 496, 8192, etc. It's a multiple of 496. So if you ask for an address, it should be page aligned, because what the operating system will return to you is always page aligned. And the size of the mapping is again page aligned. It's a multiple of the page size. So if your page is 4 kilobytes, and you can ask, by the way, to the operating system how large your pages are. If it's 4 kilobytes, then you should ask for a multiple of 4 kilobytes. Don't ask for 2 bytes. Even if you need 2 bytes, you'll take 4 kilobytes automatically. Now, typically you do memory mapped I/O because you want to map a big thing like an MPEG file or a MOV file or God knows, right? Very large things. Now, after you give the size of the mapping, you will give permissions for accessing the content, right? And because these mappings we'll see pretty soon, they are going to be shared. But for now, they will be private, but you can give permission. Then you can give the type of mapping. We'll discuss that. And what you get back, that's the funny thing, is that you get you get to actually also give, a file descriptor for the source, right? Because remember, you're mapping a file that's on disk into your virtual address space. So what you want to do is point to where you want to be in the address space, and you have to say, hey, this is where the file is coming from on disk. So disk to address space. That's the address space where you want to go. That's the file you want to read from, right? You give both. Finally, as a convenience, you could give an offset to read from a specific location inside the file. You don't have to start reading it by 0. Most of the time, of course, that's what you'll do. You would map the entire file starting at address 0. But if you want it, if you have like a, I don't know, a 1 petabyte file, you're not going to map a 1 petabyte file into your address space. You might want to map, say, 100 gigs or something like that. So you would give an offset to say, I want to map that region of my file and not the entire thing. So that's the basic idea here. All right, so here's what the API looks like. That's exactly what I said, right? Address where I want to be, length of the mapping, which is a multiple of the size page, of the page size, the protection, the flags that tell you what kind of map you're actually going to deal with, the file descriptor you'll be reading that from, so you open that via an open call, of course, and then the offset from which you want to read, which has to be non-negative. munmap, which I already show here, is fairly straightforward. You just say, hey, here is the address of a mapping I want to get back, right? I want to unmap. Note that mmap gave you the address here. This is basically the address that you got back. So this is where the mapping is placed, right? This is the base address of the mapping. And here, when you say, oh, I want to unmap that, this is the address you got from here. You pass it down to the unmap call at this stage, right? So this is what you would do. The unmap call would take the address that mmap has returned, as well as the length of the mapping, which is of course the same length you passed here, right? You cannot unmap partially. If you unmap the whole thing. So this length is the same as the one we find as the second argument inside the munmap call. That's it. That's this ID for that, the two APIs. So they're pretty straightforward. And there is no concurrency here whatsoever But what's really, really cool is that with that, we have a very simple way to do I/O because we're now accessing the file content as if it was just an array of bytes. I have a pointer to the beginning of the array, and I can use that as an array of bytes without any kind of issues. We will see that. We will see the code in a moment and actually start doing demos to play with this and see what it's like. But that, of course, is for the next video. Bye-bye.